put it on the classroom or not. Just let me try if I can put that. Uh, Thermodynamics. So second law of thermodynamics. Introduction. Where is that way? Basic thermodynamics. Okay, entropy. Yeah. Entropy. Selected problem. Okay. Okay, I'm trying to do that, whether I can put it or not. First of all, classes. So your class is basic thermodynamics. Basic thermodynamics. I think it is this one. So if I want to add something, then what to do? Stream classwork. Create. So materials. Title is entropy. Then what to do? Upload file. Okay. Upload, browse. Oh, oh. Thermodynamics. Yeah, most probably I have posted, so you can check it whether it is there or not. In your classroom, can you check that is whether that entropy and some selected problems on
Checking, sir. Yes, sir.
is it there? Okay. Anyway,
Yes, sir.
so
And
okay,
sir,
let me.
just in case I don't think you forward, but yeah, second laws notes too. Please send that.
The second law is not there. Posted. Okay, I'll post it later on. But now we have just posted
Okay.
entropy and some problems.
It's
It is
there.
available to all of you.
Yes, sir.
Okay, so in the same process, I will post sometimes. Okay, maybe after the class. So let us go to just entropy. So I am sharing that, but okay. So let us go there. Window entropy. So I think now, okay, just you can go to you can put your video off now because we'll now hear it. So I think are you able to see this?
Yes, sir.
Okay. So first thing that we'll do here is the Clausius theorem. Let's see what is this. So now look here in this diagram. So we have on the PV diagram, a process that is from I to F, that is the initial point to the final points. Let us see this one, this curve. I think you are able to follow the cursor.
Yes, sir.
Okay. So this point I, so there is a curved path like this. So it is going by this. So it is shown on this. So now what I want to do is that I want to replace this general curve or the general any process between I and F by two reversible adiabatic process and two reversible isothermal process. I think you know adiabatic process means no heat transfer, and reverse isothermal process means the temperature remains constant. So what we are drawing through this point I, we are drawing a adiabatic path. Okay, that means this particular line is a adiabatic line. Similarly to this another point, the final point F, we are also drawing another one BF, and then we are connecting them by a process AB, which is an isothermal process. So the reversible okay. So now the reversible isotherm is drawn. Okay, how it is drawn? Then a reversible isotherm is drawn in such a way that the area under the IAVF, that means, so now instead of going from I to F straight, now we'll go by this I to A, one process, adiabatic process, A to B, isothermal process, and B to F. So we'll follow this process IABF. It is basically a combination of two adiabatic processes and one isothermal process, in such a way that the area under this curve, I mean this replaced curve, IABF, and the area under the original curve IF are same. So this will tell you that the work done in both the cases are same. So when we are replacing the process IF by that combination of processes IABF, so that the area remains the same. That means work done remains the same. That means the area under the original curve and the replaced curves will be same. So now, basically now if we apply first law, then for process I to F, that is the original process, what is that? The heat transfer, that is Q is equal to delta U plus W. So that is the first law for the non-flow process. So delta U is written as UF minus UI, and this is the total heat transfer during the process IF. Similarly, W, IF is the total heat transfer during the process, your IF. Now, if you go for the other one, I mean the replaced path now, because now we have replaced this, the process IABF. So that's why again we are applying the first law, but instead of IF, we are writing that is IABF. But it is between the same initial and the final points. Therefore, the change in internal energy will remain the same. That is UF minus UY. And that is the work done in that process. And we have drawn in such a way that both the work done during the original process and the change process are same. So therefore, that is given, and your change in the internal energy are also same. Therefore, the heat transfers will be also same. That is, this gives straightforward from these two equations, that is QIF is equal to QIABF. Now, so now this QIABF can be, because this is basically consisting of three processes. There is I to A to B, and B to F. So that has been this equation on the right hand side. This equation on the right hand side has been written as three processes. There is QIA, QAB, and QBF. And out of this, the QIA and QBF are zero because these two processes are adiabatic in nature. So therefore, your QIF is equal to QBF, because in the change process, heat transfer is taking place only during the isothermal one, not during the adiabatic ones. So the heat transfer in the process IF is equal to the heat transfer in the isothermal process AB. So therefore, what we have done, that is, any reversible path can be substituted by a reversible zigzag path. Here the path is zigzag, that is IA, AB, and BF. Between the same end states, that is the initial point and the final points are same, consisting of a reversible adiabatic, no, consisting of two reversible adiabatics and an isothermal process, such that the heat transfer during the isothermal process is the same as that during the heat transfer during the original process. So any reversible path can be substituted by a reversible zigzag path between the same states, consisting of two reversible adiabatics and a isothermal process. Such that the heat transfer during the original process is the same as that transfer during the isothermal process. Okay, because here the heat, so heat transfer and so heat transfer taking place only during the isothermal process. Okay. Now let us take here. Now in this figure, we have got a reversible cycle. That the bigger one. Okay. This one, that is the somehow not curved one, circular type things. So that is a cycle, reversible cycle. Now we are breaking this into elementary cycles. How? Let's see. So now we are drawing, you can see these are the things. This curve that is coming from vertical to distance, this one, then this one. So these are reversible adiabatic, curve corresponding to the reversible adiabatic processes. And they are closed at the top and bottom by reversible isothermal processes. So the whole cycle, whole reversible cycle is broken into large number of elementary cycles. Okay, you can see in such a way that it is consisting of two reversible adiabatics and two reversible isothermal. Now you can see, if you look here, so now the cycle is something like this, So basically we are replacing the original cycle by this type of structure. But if the number of cycles are very large, then this will coincide with the original cycle. Otherwise, it will be a sawtooth type thing. So isn't it? Tooth is there, so like this. But if this number of elementary cycle increases, then it will coincide with the smooth surface. That means now we are exactly, replacing the original cycles by this number of ticks. So the smooth cycle represents a reversible cycle. The closed cycle will be divided into large number of strips by means of reversible adiabatics. So that is strip, vertical type things. Each strip may be closed at the top and the bottom by reversible isotherm. So now the original cycle is thus replaced by a zigzag closed path consisting of alternate adiabatic and isothermal processes, such that the heat transfer during the isothermal process is equal to the heat transfer in the original cycle. So the summation of all the heat transfer during this different elementary cycles will be equal to the heat transfer during the original cycle. So now what is this? What we have drawn? You have drawn basically these elementary cycles are consisting of two reversible adiabatics and two reversible isotherms. So that is basically Carnot cycle. So the original cycle is
Excuse me, sir.
yeah,
Sir, why do we need so many different elementary curves?
because otherwise we cannot. I mean, if you take one or two, the first thing is that we want to make it Carnot cycle, okay? Because
Okay.
that cycle is not known that is whether it is Carnot or not because this is a curved one. So we want some Carnot cycle, and for that we need two reversible adiabatics and two reversible isothermal process. And if the number of cycles are very large, then only that can be approximated as I mean, the original cycle will be replaced by this summation of all these cycles. Otherwise, some part will remain outside or inside, and it will not coincide with that. Otherwise, it will be a short type structure that is coming and going off like this. But we want a smooth one. So as the number of cycle increases, that will go to the smooth cycle. So
Okay,
the
sir.
original cycle is, any question?
No, sir.
Okay, I'll just give you a chance. Let me finish this. Thus, the original cycle is replaced by a large number of Carnot cycles. If the adiabatics are close to one another and the number of, okay, that we have seen, the short to the zigzag line will coincide with the original cycle. So now if you consider for the elementary cycle A, B, C, D, that is the first one you can see here. This one, A, B, C, D. So there is a heat transfer dQ1 at the higher temperature. There is a heat rejection dQ2 at the lower temperature at T2. So then for that is for the elementary cycle, first one A, B, C, D. Next you have got E, F, G, H. Next you have got some other thing. So for the elementary cycle A, B, C, D, dQ1 is the heat absorbed reversibly at temperature T1. That is the Carnot cycle heat addition. And the other one is the heat rejection at T2. So therefore, for Carnot cycle or reversible cycle, we have this relation dQ1 by T1 is equal to dQ2 by T2. So heat supplied is positive and okay. And then we can write this one dQ1 plus dQ2 by T is equal to 0. So this one giving you this thing. And similarly for the next cycle, that is EFGH, the heat transfers is dQ3 at T3 and dQ4 at T4. So in a similar way, we're writing dQ3 by T3 plus dQ4 by T4. And this will go on because we do not know the number of cycles. So therefore, if you add them, a large number of this type of equations, so this will give you dQ1 by T1, dQ2 by T2 plus dQ3 by T3 like that, and so on is equal to 0. So this gives you the cyclic integral, because if you want to finish, you have to do that for the whole cycle of dQ by T is equal to 0. And this is the thing, that statement, the cyclic integral of dQ by T for a reversible cycle is 0. And this is known as Clausius theorem. Okay, let us see any questions.
So the last equation is true for all Carnot cycles now.
Yeah, this is true for Carnot or reversible cycle. So Clausius theorem is for reversible cycle or Carnot cycle. Okay.
Okay, sir. And sir, in the curve we drawn a adiabatic curve and isotherm curve. Can
Uh,
we just randomly draw, or there is some specific thing like this curve only will be the adiabatic curve?
which
The
one that
adiabatic.
adiabatics and isothermal?
Yes, sir. Can we just randomly draw any curve and call it adiabatic or isotherm, or is there any proper way to do that?
Yeah, you have drawn it. We have drawn it randomly, but thing is that they should be adiabatic and other process should be isothermal.
So
Okay.
we have to check by that formula of adiabatic and PV equals to constant one.
Yeah, yeah, yeah.
Okay.
So then finally we have landed with this dq by t is equal to, I mean, cyclic integration of this is 0. Now let's see what does it means. Now, so now this will give you the concept of entropy, something like that. So now let us say this curve. Now here we are talking about a cycle which is running between I and F. Okay, let us consider that there are only two processes. So we are going from I to F by process R1, by path R1, I mean by a process which is following the path R1, and then we are coming back from F to I by another process which is following the path R2. So these two will make a cycle. Then what we can write? So now if you want to do this, then the cyclic integral of dq by t for this will be equal to 0. Okay, this is reversible one according to Clausius theorem. And now that you have written here symbolically, that is dq by t is equal to 0 for the entire process, which is the cyclic integral. And now that, because there are only two processes, so we have broken it into two. That is dq by t I to f following path R1 plus dq by t I mean, now it is coming back from f to I following path R2 is equal to 0. So if you take this on the right hand side, it will be minus sign. And now since R1 and R2 represents any two reversible path, so this integration I to f is independent of the reversible path connecting between, okay, I think one more line should be here. Okay, so now if you just, that is missing. যেতেই পারছি না क्या है anyway, so this should be, so now this will be written dq by t I to f following path R1 and also dq by t following path R2 from I to f. So since you have changed that minus sign into plus sign, so we have changed the limits here. Okay, I'm not able to write f somehow. So that means now we have got a property that is the, I mean, this dq by t, integration of dq by t, that is between I and f, is independent of the reversible path. Whether we are following path R1 and R2 doesn't matter. So long I and f are remaining same, these two are equal. So this shows that there exists a property of a system whose value at the final state f minus its value at the initial state is given by integration of dq by t I to f. And this property is called entropy and is denoted by S. So basically the concept of entropy came from the, from the mathematics. Okay, that is, since after that we are not able to progress, so let us define here a property which is basically a point function, not a path function, because it depends, that is, its change depends only between the initial and the final points and not on the path. So therefore, dq by t is equal to sf minus si. And if they are very close to each other, then in the differential form, we can write dqr by t is equal to ds. And since we are talking about the reversible path, that's why we are writing that. So, okay, we'll come to this afterwards. So ds is an exact differential because s is a point function and it is a property. So the word came from the Greek word troop, means transformation. Okay, since entropy is a point or state function and the entropy change is independent of the path followed, the non-reversible path is to be replaced by a reversible path to indicate the evolution of entropy change in the irreversible process. So what I'm telling is that, so that is basically dqr by t ds, or you can integrate that, but that is only possible when we have a reversible path. We cannot integrate over an irreversible path, but it may follow or it follows a irreversible path between the same state point. So the thing is that if you want to find out what is the change in entropy, or what is ds for that, then we are integrating dqr by t between I and f. Now, if it is an irreversible process, then also we have to do the same thing. That means you have to replace the irreversible path between the state points I and f, and then you have to integrate over that, because that integration can only be carried out over the reversible path. And since entropy is a point function, it doesn't matter what path it followed, whether reversible, irreversible, whatever it may be, the change of entropy will be same. So that's why for the calculation of entropy between two state points for an irreversible path, it is being replaced by the reversible path, and then the entropy is calculated. So del sf minus si is equal to dq by reversible. So we are doing the same thing, and that is also the change in entropy for the reversible path between these two states point. Now, so that we have shown here, this is a reversible path, and this is basically what is called the irreversible path. So we can see that although they are not following the same path, but the entropy change is same because it is a point function. So now, if you come to this, okay. Now, this will give you, now what we have written, that is dq by t is equal to ds. dqr by t is equal to ds. Therefore, we can write dqr is equal to tds. And then if you integrate, then the left-hand side, that is dqr, okay, that is inexact differential. So integration of that will be total heat transfer between state 1 in the process 1, 2. Integration of dq between 1 and 2 will not give you the q2 minus q1 because it is inexact differential. Rather, that will give you the total heat transfer during that process. And that is equal to integration of TDS. So if you can integrate that TDS, that will give you the heat transfer during that process. Now look here. So we have got a T temperature. Okay, that's why this temperature versus entropy diagram is very popular diagram corresponding to, I mean, similar to your PV diagram. So temperature versus entropy, TS diagram is very important in thermodynamics. And if you look here, so a process is taking place from initial point I to the final point F. And it is following this path, that is the reversible path. It is following the dotted line, that is the irreversible path. Okay, one more thing is that you have to, in a TS diagram, if the process is reversible, then you have to show it by dotted line, not by hard lines. So that is the general concept. So any irreversible path on the TS diagram should be shown by a dotted line, not by a hard line. So that will differentiate that, or that will tell you that it is an irreversible path. So now look here, in that process, I to F, now what is the integration of TDS? So that is nothing but the area under that curve. So you mathematics, you know. So when you go from I to F, the change in entropy in both the cases are same between this path and this path or any other path. But the area under these two curves are different. Okay. Area under these two curves are different. Hello. আচ্ছা আচ্ছা, ওখানে শুধু কি লিখবো, শুধু ক্যান্সেল লিখে দেবো না আর কিছু করতে হবে? হ্যাঁ, আমি থাকতে হবে, যে পলিসি আমাকে দিয়ে এসেছিলেন আপনি, বাবা সেটা খুঁজতে হবে, আগে বললে আমি খুঁজতাম। আপনি কখন আসবেন? ঠিক আছে, আমি দেখছি তার মধ্যে খুঁজে। হ্যাঁ, আমি ফোন করছি। Okay, so then, okay, so that is the case. So area under the TS diagram will give you the heat transfer. In a similar way, area under the PV diagram is the work done in a process. So now, so that's why temperature versus entropy plot is very important. Now look here, this is a temperature versus entropy diagram for an isothermal process. That is from I to F. So the process is taking place at a temperature T, and the entropy has changed from Si to SF. Now the area under this diagram will give you the heat transfer. So obviously Q is equal to here what? That is T multiplied by SF minus Si.
Final minus S initial.
Hello?
Yes, a T into S final minus S initial.
Integration of T ds, T is coming out of the integration sign, okay? Because T is constant, and therefore in this case, the T into SF minus Si, that is this area, which is the heat transfer during the process. Okay, now if you go for a reversible adiabatic process, then what is that? That Q is 0. So for a reversible adiabatic process, dq is 0, therefore ds is equal to 0 or s remains constant. For a reversible adiabatic process, s remains constant, and that is also known as your isentropic process. So the process in which entropy remains constant is known as your isentropic process. So a reversible adiabatic process is an isentropic process. And here also, and now if you look here, so TS diagram, so this is the vertical line, and the area under the TS diagram is 0, because the entropy change is also 0. So here Q, okay, that is the other one. So in this case, entropy remains constant, therefore the heat transfer is also 0 in a reversible adiabatic process. This is of course for a isothermal process. And now,
Sir, in the previous graph, what is in y-axis? No. Next one.
yeah,
Yes, here.
it is T, this temperature and entropy. X-axis is entropy, y-axis is temperature. That's why it is known as.
No, T is not properly visible. That's why I'm asking.
There is no need of properly visible, because in the meantime you know what I'm discussing and this, right?
Okay.
So that is temperature versus entropy, right? Because we are not talking about only TS diagram. So in all the cases, the y-axis is your temperature and the x-axis, the other axis is your entropy. Now we'll show here a Carnot cycle on the TS diagram. Now look here. So if you remember, Carnot cycle is consisting of two reversible adiabatic process. and 2 reversible isothermal process. And during the isothermal process, in one process at higher temperature, heat is added, and in the other temperature, heat is rejected. So if you look here, it's T1 and T2. So at temperature T1, this is an isothermal process, so it is horizontal line. Q1 is added. Next is 1 to 2. That is your reversible adiabatic process. So on the TS diagram, it will be a vertical line. Similarly, 2 to 3, another isothermal process where heat rejection is taking place at temperature T2. Therefore, that is a horizontal line. And similarly, 3 to 4, that is another one where the work is done. So now, if we write down in terms of this, let's see what is happening. Now, what is Q1 here? Anybody can tell?
Q1 is equal to T1 into ds. Integration T into ds.
Integration is simplified here. What is that? After the integration, what is the result?
T1 into ds.
DS প্লিজ বললে হবে না, এখন বলো ঠিক করে বলো, what is?
Sir, T1 into S1 minus S4 minus S1 minus S4.
Yeah, so Q1 is equal to T1 into S1 minus S4, right? And similarly, Q2 is equal to
T2 into S2 minus S3. It will be negative.
T2 into S2 minus S3, right? Okay?
Yes, sir.
Because here the heat is rejected, that's why we are taking the this first point. So now that Carnot cycle, now we have, so eta Carnot, I think you know that is 1 minus Q2 by Q1 is equal to 1 minus Q2 by Q1. And now let us put the value of T1 here and Q1 and Q2 in terms of temperatures and entropy. So S1, T1 into S1 minus S4 minus T2 into S2 minus S3 divided by S1 minus S4. And you can see that S2 minus S3 is same as S1 minus S4, right? So the entropy change in both the cases are same, therefore they are getting cancelled, and you are getting the well-known expression for Carnot cycle, that is 1 minus T2 by T1. And of course, you can get that is W net Q1 minus Q2 is equal to, okay, there is Q1 minus Q2. So if you write in terms of temperature and entropy, it will be like this.
Sir,
Okay,
sir, in adiabatic process, ds will be always 0 or it has some value. In
adiabatic process.
Yes, sir.
I mean, you are telling that whether entropy change will be 0 or not in an adiabatic process.
Yes.
That is your question, most likely. Huh?
Yes, sir.
What is your answer?
Sir, I don't know. That's why I'm asking.
So who knows, or who will be able to give that answer?
It is always 0.
Sir, 0. Always 0.
DQ is always 0 in adiabatic
It is
reversible
always 0,
process.
that's why.
No, ds. I'm talking about ds.
Q is always 0, so DS is always 0, no?
Any other answers? Okay, let us see what is his question first. Okay, I think we will not proceed anymore, so let us stop. So come back to your with camera on the screen. All of you come back. All of you come back by opening your camera. So roll number 105. Roll number 105. What is his question? Tell me. What is the question that is asked by him? You have to say something. 105.
Yes, sir.
It is nothing written on that. It is what is the question asked by him. That is the thing.
I don't know.
So what are we doing when he is also, because this is also important. It is not my lecture only, because what are the questions other people are asking and what are the answers they are giving. That is also important. Roll number 97. So what was the question asked? 97. Are you there? He has just asked one question. Who has asked? Roll number 34, na?
Yes, sir.
দেখেছো? So there must be, you must be careful. Who will be able to answer? Answer means what is the question asked? Then the answer will come.
Sir, sir, I think S is constant
Huh?
because sir, S will be constant.
No. I am not asking about the answer. I am asking about the question. What is the question asked?
Sir, so he's asking about that if DQ is 0, then DS is always 0 or not.
Are you asking that questions in so details? What is the question? Roll number 34.
Sir, in adiabatic process, dq is always 0. So if you ask the question like,
No, you don't explain.
dq
What is
is
the
0,
question?
sir, in adiabatic process, ds will be always 0 or not?
Yeah, that is the question. So in adiabatic process, ds will be always 0 or not. But here we have shown that is the entropy change is 0 in an, isn't it, in the curve, and that's why it is a vertical line. Rule number 104. Any comment on that?
Yes, sir. Sir, in adiabatic process, no heat is transferred, so entropy change in entropy will be 0.
Rule number 16. 16.
Yes, sir.
Ah. So what is your answer?
I said in adiabatic, I think in adiabatic process there is no heat enters or leaves this system. So here heat remains constant. So the entropy change should be 0.
Heat remains constant. That doesn't have any meaning. Okay, so the answer is something like this, that may not remains constant. Okay. Any comment?
Sir, please repeat. May not be 0.
May not be 0. Then what it can be? Basu, what it can be then? If it does not, if it is not 0, then what it will be? I mean, if entropy does not remains constant, then what it will happen? Either it will increase or decrease.
So from the previous knowledge, I know that during any process, entropy should decrease. So logically, using the formula, the entropy must be 0 as dq equals to 0. But
Okay.
let's see.
So let us see here. What you have said here is that this is for a reversible process, right? So for a reversible adiabatic process, entropy change will be 0. Okay? Now we'll see afterwards, if the process is not reversible, it may be adiabatic, then entropy change may not be 0. Okay, that will come later on. But definitely for a reversible adiabatic process, the entropy change will be 0. And that process will be known as your isentropic process also. Okay, that does not mean isentropic means entropy remains constant, like your isothermal, isochoric, like that. So that is the case. So let us, if you have any other questions, you can ask in the meantime. So
Sir,
that, yes.
if the process is irreversible adiabatic, but ds will be 0, then then what we call the process isentric process or not?
Yeah. If entropy remains constant, so whatever may be the nature of the process, whatever nature, So that will be known as your isentropic process. But we'll see afterward that does not mean it will be adiabatic. Okay. So, okay. Okay, we come to that in details afterwards, why that happening and what is the reason behind that. So that we'll
So,
see afterwards.
so what does this dq by t specifies? Like this is just a random quantity, or does it specify anything?
What?
Like dq by t, that entropy, the formula of
Hmm.
entropy. We just heard
Hmm.
like we just you just thought like came to that formula through Clausius theorem.
Hmm.
But does it specify anything, or it's just a random term?
No, no, that is actually what I am saying is that, mathematician is just they are going calculations and finally they come across with the term dq by t, and then they gave it a name to that, that is entropy. So because that is becoming, that is a exact differential. So then they thought that there must be some property, and that is denoted by dq by t, and let us give that as ds. And afterwards, they are trying to find out that what is entropy. Okay, see that the entropy that will give you the randomness in the system, the order of disorder, all these things. Okay, so these things are there. Uh, Actually, as I told you, that it is something which is something abstract. It's not like the property like your pressure, volume, and temperature, which can be measured. Rather, you have to calculate it using some formula which contains the measurable quantities, pressure, volume, temperature, etc. Okay. So the concept of entropy is somehow, you know, uh, difficult. So people understood, rather understand according to their things. So that's why you can read some good books if you're really interested to have some idea. I don't know whether you at least have some idea. So you try to read those books if you're interested, Sengel's Bowles or Moran, etc. Right? Okay, so we can have more discussion on this, and there is an endless discussion, but we have to do that. So in the meantime, let us take that attendance. Uh, so how many people said there? Only 72. Why? So Orno, Ujjwal, Vasu, all are there. Four, up to four, it is all right. Yeah, let us see who was left. I'll just ask you. 1, 2, 3, 4. Roll number 5. 5 is there. 5. Very. 5. 6 is not there. 6 has left or not? Shomiron Mahato, do you have any idea?
Sir, he is having network issue due to flood in his region.
Okay, ठीक है. Okay, I'll just check it. 7 is there, 8 is there. 7 is there. Okay, I have talked to the HOD. So now those who have regarding your mini project, I think some people have left. So if suppose there is a group of 4, if so one people is left, so he will be taken from that students who have joined. So I think as such, so by this way that the vacant places of the existing groups will be filled up by taking 8 of them from that, and the rest of them will form maybe another 2 separate groups. Okay, is it clear? So actually those who have been allotted guides, their guide is not going to change because one student has gone, so you'll get another student from there, and you have to create 2 more new groups for the rest of the new students. Okay, roll number 9 is there or not? 7, 8 is there. 9, 10, 9, 10, 9, 10, 11, 12, 13, 11, 12. Monisha, where is Monisha?
Present, sir.
Where are you? Open your video.
Sir, my video is on.
Video is on, but it's not coming here anyway. Okay, ठीक है. So Thing is that you are not able to attend most of the classes.
No, sir, I didn't attend the last class.
No. It is blank. I have seen it here. Just the record says that it's like that. So at that time I was checking, maybe you are absent, but that it is clearly shown that you are not present in many classes. Anyway, so try to be present in all remaining classes. Okay.
Okay, sir.
16, 17, 18. 16 is Purva, 17, 18 is Abhrojit. After that, 20. Ajay, what about 19? Alex has left. Okay, let me do very quickly. So read to 21, 22, 23. 21, 22, 23, then 25, 26, 25. Ajay, who is 25?
Yes, sir.
Shitanshu Patro.
Yes.
25, come to the picture with, where are you?
Sir, here the video is on.
Huh?
Sir, my video is
25.
on.
But why you are absent in most of the classes? Only the last class you are present.
Yes, sir.
What was any problem?
Sir, yes, sir. I was actually out of station.
Okay, so now try to attend the rest of the classes. Okay.
Okay, sir.
27 and after that 29. Then 27, 29. Then 30. Who is 30? 30 is not here. Okay, 31, 32, 33, 34. 31, 32, 33, 34, 35. 35 has left or what? Enakthi Shah.
She changed her department.
Yeah. Okay, ठीक है. So I'll check it from that list. So 36. So 37, 38. Ajay, who is 37? Novendu.
Yes, sir.
Where are you? So your attendance is also not good.
Okay, sir.
Why? The problem क्या है? No network issue, huh? Any other problem? What is the problem? 41, 42. बोलो. क्या problem क्या है?
Sir, actually network issue.
Network. কোথায় থাকো তুমি? Where are you staying now?
सर कृष्णनगर से थोड़ा दूर.
Krishnanagar is a good place. There should not be any network problem.
उससे थोड़ा दूर सर, गांव में.
अरे कौन सा गांव में है भाई?
धुबुलिया.
Dhubulia that is also on the highway, isn't it? What was your school in higher secondary?
कृष्णा कॉलेजिएट स्कूल.
তবে ভালো স্কুলে পড়েছো?
হ্যাঁ স্যার.
ধুবুলিয়া তো কৃষ্ণনগরের পরেই, তাই তো?
হ্যাঁ স্যার.
তবে ধুবুলিয়া খুব একটা খারাপ জায়গা তো নয়।
কিন্তু স্যার এখানে অনেক দিন ধরে মানে বৃষ্টি চলছে তো ওর জন্য একটু নেটওয়ার্ক ইস্যু.
আচ্ছা ঠিক আছে, দেখছি এর পরে কতদিন নেটওয়ার্ক ঠিক থাকে। হ্যাঁ, লেট মি সি দ্যাট। ওকে, so you try to attend the rest of the classes, okay?
Okay, sir.
Then your network problem will be solved, otherwise it will remain.
Okay.
Then 59, then 61, 61, 62, 63, 64. 61, 62, 63, 64. Ritik Sharma.
Yes, sir.
Your attendance is also not bad, but also not that good. Anyway, so try to improve that.
স্যার অ্যাকচুয়ালি আমার ল্যাপটপ রিপেয়ার করে দিয়েছিল, তাই বলে 2-3 দিন বন্ধ ছিল।
ঠিক আছে। Then what is there? 64, 65 is there. 65, 66, 68. 65, 66, 68. There is no 67. And 71, 72, 74. 71, 72, 74. 74, 70, 75. Juvaraj Shankar, he has left, most probably. Not known. You have to check it, who has left. So 77, 81, 77, then 81, then 81, after that 82, then 84, 85 is also there, then 86, 87, 89, 90, 87, 89. Who is 89?
Sir, me.
Yeah, you are not attending regularly. So try to do
Sir,
that.
yes, sir. I had a viral fever last week.
अच्छा ठीक है चलो 92 94 92 94 95 96 97 and 98 97 and 98 and then the other people. What about the other people? Okay, I'm just not listed here. I have added you in the classroom. So those who have joined, so you have been added to the classroom. So 99, then who is that? 100,
Yes, sir. Received the invitation.
101, 102, 103, 104, 105. 105. So 106 is there? No, 107. 107.